Okay, we'll begin at that question. Okay, so if not, let me write down the equations again that we had obtained so far. And here, let me give some. I'll just give some definitions. So N naught I have just introduced today, just so that you don't have to write this 0.73 times NB many times. This is the total number of electrons, okay, or equivalently total number of protons. Okay. And X and Y we had already introduced earlier. So X was given by the number of free protons divided by N naught. And Y was the number of N1s hydrogen atoms divided by N naught. And what you have described is how to calculate all of these quantities. Okay. So you have described how to calculate all of these, how to calculate the coefficients. Now there is one point I should make here, okay, which I didn't discuss, is that these rates, okay, these are microscopic rates, right? Alpha, gamma 2s, gamma 2p, these are microscopic rates, okay, and the others are where you obtain by detailed valence. So these need to be calculated in the presence of a path. Okay, and let me just describe how it makes a difference in the presence of the thermal bath. Okay. So to see why this is important, this is relevant, okay, recall that for processes with neutrino final state, with new final state, we had to multiply by 1 over 1 minus 1 plus e to the minus e nu over t. And physically, this was the probability. This was the probability that the final state, final neutrino state that you are transiting into, that state is unoccupied. So this factor was, so you have to do the microscopic calculation and then you multiply by this, okay, to take into account the possibility that the final neutron state may be occupied. Okay. And in that case, that process cannot take place. So you have to multiply by this extra factor. So here you have photons. Okay, so for bosons, you have a similar factor. So for bosons, we have a similar factor, but here it enhances the probability. Okay, so it's basically 1 over 1 minus e to the minus e over kt. This is e gamma over t. So this is enhances the process, which basically means if the final state is occupied, okay, then it's more likely that the system will go there. Okay, because that's what Bose statistics gives us. So this basically follows from statistical mechanics. So this is sometimes called the induced emission, induced process, right? Or induced emission. Okay, and the corresponding coefficients are also sometimes called this Einstein's A and B coefficients. So this factor is not very important for the for gamma 2s and gamma 2p, and the reason simply is that the E gamma there was B1 minus B2, right? And for the temperatures that we are dealing with, e to the exponential minus B1 minus B2 by 2 is very small. Okay, so this factor can be ignored for gamma 2s and gamma 2p, but not for the E minus P capture, okay? But not for E minus P going to H plus gamma, because here it could land up in a highly excited state of the hydrogen, okay? And the corresponding gamma can have low energy, okay? And for this suppression, this factor will be important. Okay, so for this we need to take this factor into account for this.
So
Yes, go ahead, please.
why is this important for the output photons? It should be important for the input, like incoming scattering photons.
Yeah, except that here there is no incoming scattering photon, right?
Yeah, so it's not important.
Yeah, but just because for the neutrinos, this factor was important because the final state neutrino could have been occupied, right?
Yeah, but there we have a Pauli exclusion principle for fermions.
Yeah, so for bosons, we have an opposite principle. Okay, we don't state it as a principle normally, but it follows from statistical mechanics that for bosons, if a state is occupied, the probability that you go into that state gets enhanced. Okay, this is what is sometimes called the induced emission. Right? If there is a photon, then it's more likely to produce a photon. Okay, than if it was decaying in the vacuum. So I'll not try to go into the details of how this factor comes, but this is a factor that is present for bosons. Okay? And this is what, as I said, what is sometimes called this Einstein's A and B coefficient, that is spontaneous emission versus induced emission. So one would be the spontaneous emission, right? If it was just one, it will be spontaneous emission, and the difference is what we sometimes call the induced emission. That presence of a photon makes it more likely that it will emit a photon.
Does this happen for other bosons?
Yeah, for all bosons. This is part of the Bose statistics.
Yeah, but I don't see a reason why we do this.
Yeah, but what I'm saying, this follows from statistical mechanics. I mean, it's not obvious from this. I mean, because we state this for fermions, the fact that the wave function is antisymmetric, okay, we state it as Pauli exclusion principle. So you can see it reasonably clearly why there should be such a factor.
Yeah.
But for the bosons, the point is the different bosons are not independent, right? So the wave function has to be symmetrized in the final state photon, and the photon may already be present. That may already be present. Yeah. So the final state wave function, that state that you are aiming for, right, is not quite the state that you would aim for in the vacuum. If all the photons are independent, then what you are saying is correct, right, for distinguishable particles. But the final state is symmetrized. The wave function that you will be using now will be symmetrized with respect to all the photons of energy E gamma, right?
Yeah, but the photons are actually sort of independent, right? I
No,
mean,
they are not. They are independent in the sense they don't interact.
yeah.
But their wave function is not independent.
Uh,
Right? Because that is symmetry factor.
okay.
So what I'm saying is that if it was recurring in a vacuum, the state that will land up in is not, and if you are doing it a thermal bath, right, the state that you are landing on, the second state is not a product state. It's not a product state of the state in the vacuum together with the thermal bath wave function. And the reason that it's not a product state is because the wave function has to be fully symmetrized in all the photons.
Yeah.
From this, you can see that there could be a difference, right? Because it's not really independent. The wave functions are not independent. And that translates to a factor like this. Because otherwise, there will be no induced emission, right? I mean, this whole term induced emission basically reflects this. That the presence of a photon actually makes it easier to emit a photon than it would be otherwise. It's exactly opposite to that of a fermion.
No, this is the n gamma plus 1 factor, right? Number of photons plus 1. 1 is due to the spontaneous emission and n gamma is due to induced emission.
Yeah, so the ratio of this is exactly like that, no?
Yeah.
I mean, the ratio between, so you can write this as 1 over this plus or minus, plus or, yeah. So 1 over this plus e to the minus e gamma over t. Maybe I'm not doing things correctly. What is okay? Anyway, so one has to work this out correctly.
This is the factor, yeah.
But it's roughly this ratio, right?
Yeah.
That is coming in here. So that's this enhancement factor. And as I said, you can see this, okay, or you can understand this. At least you may not be able to get exactly this factor, but at least the fact that there should be a difference, you should be able to see. Right? Because the final state wave function is not the same as the product wave function. Is this okay? Are there other questions? Okay, so the other complication, of course, is that I mean this alpha involves transition to any of the states, right? Transition to any NL state with n greater than or equal to 2. Okay, so it needs some of our final states. So this, I'll not discuss much of this, but you can find a more detailed discussion in Weinberg's book, okay, where you'll also find references for this. Okay, the other point I wanted to emphasize, and that will be important for what we are going to discuss next, is that these equations that we have written, dx dt equal to something, okay, dy dt equal to something, and you can write a similar equation for d dt of 1 minus x minus y. Okay, this is the fraction of states that is in the NL states. Okay, this is just can be obtained just from taking the sum of these. So the right hand side, okay, so let's compare this with what we would get by assuming thermal equilibrium, right? This is what we did earlier. Now, the assumption of thermal equilibrium basically amounts to setting the right-hand sides to 0. So this solution, right, if you take the solution that is given by thermal equilibrium using the Saha equation, then this basically sets the right-hand side to 0, sets all the RHS to 0. Okay. Because after all, we determine these coefficients beta and E by detailed balance, right? By assuming that thermal equilibrium, the rates will vanish. Okay. So you can easily check that thermal equilibrium sets this to 0. Now, you can see that this is strictly not a solution to these equations. Why not? Because in thermal, suppose you take the solution that is given by in thermal equilibrium. This X and Y will still be functions of T. Right? And T is time dependent. So if you set the right-hand side to 0, that is the thermal equilibrium, and substitute in these equations, you will find that this dx dt, in fact, it doesn't satisfy this equation because dx dt is non-zero. But the point of using the thermal equilibrium solution is that the time dependence, that T dependence of the temperature, is much slower than the reaction rates. Okay. That's why this is still an approximate solution to the equations of motion, to those equations. I can put it in another way. Okay. Let me write it this way. Suppose you write dx dt equal to something and dy dt equal to something. I'm just writing this third equation also, although it's not independent. Suppose I just take these equations, okay, and multiply these by some large number, large positive number, right? Say lambda 1, multiply this by lambda 2, and multiply this by lambda 3. Then in the limit that lambda 1, lambda 2, and lambda 3 goes to infinity, the solution will be given by that obtained assuming thermal equilibrium. Because what's going to happen is that if these are large numbers, then dx dt will be so large that it will be driven towards its equilibrium value very fast, right? So that this bracket will be 0. So till this bracket becomes small, dx dt will continue to change towards the equilibrium value. Similarly, till this bracket becomes small, dy dt will continue to change towards its equilibrium value, and so on. Okay. So the thermal equilibrium formula is valid when the individual terms inside this are large, okay, and that's the reaction rate, and that's the limit in which the thermal equilibrium is a valid assumption. That and we stated it quantitatively by saying that these individual reaction rates should be much faster than the Hubble expansion rate, okay, because T dot over T basically follows the Hubble expansion rate. Now, in the present context, okay, this assumption is not valid, and that's why we are doing this. But it turns out that part of this assumption is still valid, okay, and that is the following, okay, at least, well, it's approximately valid, of course. Whenever you are using thermal equilibrium, you are already making an approximation, right? Because you are assuming the reaction rate is infinite, but of course, the reaction rate is not infinite. So what one can verify, okay, and this I'll leave as an exercise. So that's in fact homework problem 1. So the homework problem 1 is asks you to solve the coupled equations, right? Coupled equations for dx dt and dy dt. But what one can verify is that the reaction rates for this process, okay, so they look at this, so this is the middle one, right? These are NL states. Now the rate of reaction, the rate of transition from the E minus P system to this NL states, and from the NL states to the 1S states, those are fast enough so that this reaches a dynamical equilibrium. Okay, so that's something that you can in principle verify by solving this. But I'm just trying to, I'll just assume that this is true and see what happens. Okay, see that we'll see that the equations can be further simplified if you make that assumption. So let me state this again. So if you have, look at this three-state system. Okay, this is 1, this is 2, this is 3. So 1 is the E minus P pair, 2 is the NL state with N greater than 2, and this contains a 1S state. And if you remember, the transition takes place between 1 and 2, and between 2 and 3. But 1-3 transition is negligible. Okay, that's what we are ignoring. So what one can show is that 2 reaches a dynamical equilibrium. Okay, so you can assume, okay, it's like using thermal equilibrium, we are assuming that the right hand side of the equation that determines 2, which is the 1 minus x minus y, that actually can be set equal to 0 because there are 2 large terms which almost cancel. So this reaches a dynamical equilibrium. Okay. And effectively what happens is that 1 flows to 2, 2 flows to 3. This is a net flow. Okay, 1 flows to 2, 2 flows to 3. Okay. In a way that 2 maintains its density. Okay. But of course, as time progresses, right, the temperatures and everything else is changing. So of course, the density of 2 will change a little bit, but it remains more or less constant. Okay, the number density of this system particles in state 2 multiplied by lambda cube, that remains more or less constant. Okay. So 1 to 2 basically gets balanced by 2 to 3. Okay. So this is the analog of this deuteron bottleneck, right? There you had argued that once the temperature comes below a certain value, okay, what's going to happen is the deuteron density is going to remain more or less fixed. Okay. And then the excess protons and neutrons will combine into deuteron, and that more or less immediately gets converted to the other heavier nuclei. Okay. So this system 2 here is playing roughly the role of the deuteron in the nucleosynthesis. So this means that ddt of 1 minus x minus y is almost 0. Okay, that this remains constant. Okay, by setting this equal to 0, we are using the fact that 2 reaches some kind of dynamical equilibrium. Okay. So this means that the right hand side, RHS of dx dt plus dy dt can be set to 0. Okay. Again, as I said, you should really try to verify this because you have got the full set of equations. So once you put in the numbers and if you evolve them, right, you will see that in this is small. Okay, so whatever is produced in system 2 is more or less immediately get converted to system 3. But if we do assume this, then we get a further equation, minus alpha x square n naught plus beta over f of t times 1 minus x minus y is minus gamma 2s. Okay, this I just took from the equations that we saw in the first slide. Okay, so this is the rate of change of x. Okay, now, and this is the rate of change of y. Okay, so if they are equal and opposite, then the system 2 remains unchanged. So the idea is that we will try to use this equation to eliminate y. So we'll get a equation in terms of x, and then we are going to use this equation, the dx dt is given by this. Okay, that's the way we are going to solve this. Okay, so that instead of having two variables, okay, two differential equations in two variables, we have a single differential equation in one variable, okay, which is easier to see, and one can get a little more insight with that. Okay, and clearly, if you want to now solve it numerically, one equation is easier to solve than two equations. Okay, other questions? Okay, so the way we are going to solve this is to write this one as E times or minus E times 1 minus x minus y plus E times 1 minus x. And then bring all the 1 minus x minus y factors on one side so that we can get 1 minus x minus y as a function of x. So let's see, maybe I should be able to do it here because so this will give you, we are bringing, so 1 minus x minus y, right? We are bringing it, say, on the left hand side. So 1 minus x minus y, or 1 over f of t times 1 minus x minus y times beta plus gamma 2s plus gamma 2 plus 3p gamma 2p gamma 2p plus e times f of t equal to alpha x square n naught plus e times 1 minus x. Okay, so this is the equation I'm going to use. So the idea is that now we have this dx dt equal to this, okay, and then 1 over f of t times 1 minus x minus y, I'm going to substitute from here. Okay, because this gives you, you can just divide by this and we'll get the 1 over f of t times 1 minus x minus y. So in the next slide, I'm going to basically do that substitution. So dx dt is minus alpha x square n naught plus beta over f of t 1 minus x minus y. And if you make that substitution, then you'll get this to be minus alpha x square n naught plus beta times alpha x square n naught plus e times 1 minus x over gamma 2s plus 3p gamma 2p plus beta plus e or e times f of t. Let's just go back. Okay, e times 1 minus x here is fine. So here we got e times f of t, right? Because it's 1 over f. E is not multiplied by f of t, so e times f of t. Now what you are going to do is to make an approximation. Okay, so for this you recall that E is given by gamma 2s plus 3p gamma 2p e to the power minus b1 minus b2 by t. Okay. So in the temperature range of interest, right, this is a very small number. Okay. So this is much smaller than gamma 2s plus 3p gamma 2. And f of t, of course, is just a finite number, right? We saw that it's like of the order of 4, okay, coming from the 2s and 2p systems. So because of this, in the denominator, we can basically drop this. Okay, we will not worry about this in the denominator. But in the numerator, we cannot really drop this. And the reason for that is that we are comparing, see, here you have the x squared that multiplies the rest of the terms and 1 minus x multiplies z. Okay. We are eventually going to analyze the system when x becomes very small. Okay. And when x becomes very small, then the E may be comparable to x. Okay, that this term may be comparable to this. Okay. So from the numerator, we cannot drop E, but from the denominator, we can drop E. Okay, and that's the approximation we're going to make. So if you take that, then we get dx dt. Okay, we are not going to now try to combine. So we get alpha x squared n naught or minus alpha x squared n naught okay, let me just check the sign here. Yeah, alpha x squared n naught plus e times 1 minus x. So here in the numerator, you have the denominator, you have gamma 2s plus 3p gamma 2p plus beta. And in the numerator, we have gamma 2s plus 3p gamma 2p. Right? Plus, we have this beta e times 1 minus x over this, but for e now, we are not going to substitute this. So we again get gamma 2s plus 3p gamma 2p over times beta times e to the power minus b1 minus b2 by t. Is this clear? Right, so I just combined the alpha x squared n naught terms from between these two, and then this one I wrote by substituting for e. So now we are going to also substitute the expression for beta. So let me write that here. So beta, if you remember, we got by detailed valence, so as alpha times mat over 2 pi to the power 3/2 e to the power minus b2 by t. So we are going to substitute here. So this e to the minus b2 by t will cancel this e to the plus b2 by t. And we get just e to the minus b1 by t times this mat over 2 pi to the 3 by 2 factor. So I'm now going to connect everything and write things neatly in the next slide. And you can also see that this factor is common, right? So that you can take out. Okay, and beta is proportional to alpha, so alpha can also be taken out. Okay, so in the next slide, I'm going to do that. Are there questions on this?
Also, where did the linear and X term go?
Linear in X term. Oh, 1 minus X. Yeah. Sorry. It should be multiplied by 1 minus X. Is this okay?
Yeah.
Okay.
Also, one thing,
Yes.
our boundary condition I would have thought is x equal 1 at t equals 0 and y equals 0.
Yes, that's right. So
Yeah,
that's the
but that is not exactly compatible with the constraint.
yeah. So of course it is never compatible with the with which constraint you are saying.
The one in the previous page that we got through.
So this of course requires that the system 2 is in thermal equilibrium, is in dynamical equilibrium, right? You certainly not
Exactly.
initial. Okay. But initial
So should we come up?
Sorry.
Yeah. So like in the hello.
Yes. Yes. Go ahead.
I think yeah, I couldn't hear you for a bit, but I was saying that maybe like in the deuterium case, we should get a evolve the system non-equilibriumly and then see what values it like fixes.
Yeah, but except that because most of the 1s formation takes place in this regime, right? The difference doesn't make that. I mean, is not really important, right? You're right. That I mean, correct thing to do, of course, will be to evolve this x and y to the individual differential equations. But
Yeah.
get an approximate solution, right? This is good enough. Okay, and basically, I think you find that this gives results which are about 10% different from the actual numerical results. If you use
Like so, do we still use the initial boundary condition as x equal 1 at t equals 0?
yeah, that's what we'll use. Okay. Except that x will remain 1 for a long time.
All right.
Okay, so when x starts differing from 1, right, this condition sets in.
Okay.
Any other question? Okay, so the final equation that we get is dx dt is gamma 2s alpha, I think, comes out. So alpha here. Okay, that b2 got cancelled, so you are left with minus b1 by 2. And now I'll write this one more time in a simpler way. Let's take n naught out. And I'll write this is minus x squared plus s inverse times 1 minus x, where s is basically the inverse of whatever comes here. So it's n naught times met over 2 pi to the minus 3 half. e to the power to 1 by t. This factor, if you remember, we had seen earlier while studying the result assuming equilibrium. And there the equilibrium condition for x that we got was x squared equal to, or s times x squared is equal to 1 minus x. This was the condition derived using assuming thermal equilibrium. So this again confirms whatever we had said, okay? Namely that setting the right hand side equal to 0 corresponds to thermal equilibrium. Right? Here we did it in 2 steps. Well, we haven't done this one, right? Because there, of course, we could have used thermal equilibrium. So the idea is that now we can simply use this to solve for x. Okay, and as I said, you could certainly solve the coupled equation of x and y and get the result. Okay, but this gives a reasonably good approximation to the original set of equations. As I said, I think the difference is about 10%. Okay, otherwise this does quite well. Okay. So effectively, what it is doing. So this equation is driving x towards thermal equilibrium, driving x towards equilibrium value. But the problem is that the rate is not fast enough to establish immediate equilibrium. Okay, and the reason is again that it has to go through this NL system. Okay, that there is no direct transition from the free electron proton pair to 1s. Okay. And because it has to go through this NL system, okay, the occupancy number, right, in equilibrium, the occupancy number of NL states is much lower than the occupancy number of the 1s states. And because of this, okay, because of the low occupancy number of the NL states, this process is slow because you have to first form NL states, and then even though that forms fast, okay, according to what thermal equilibrium tells us, okay, the equilibrium value itself is small enough. Okay, it's small, and hence it cannot just build up enough numbers to supply to the 1s states, supply to form 1s states. So that's essentially the physics of why this process is slower than what the equilibrium gives us. And so I'll just quote some number, okay, and you can work out the full table yourself by solving this equation, or you can look up the table that Weinberg gives. So just as an example, okay, so overall the rate is slower. So overall one finds that the rate of decrease of x is slower. One we get assuming thermal equilibrium. So for example, so if you take omega b h square equal to 0.02, that's the one for which you got the earlier table, right? So thermal equilibrium gives x about 0.00493 at 3000 K. but the differential equation gives x as 0.154 at 3000 K. Okay, so it happens slower. Okay, and that's what we find by doing this differential equation analysis. And if you do the full numerical analysis, you get about 10% higher values than this one. Okay, this is based on the single differential equation dx dt. But if you do the full analysis, you get about 10% higher values than this one. So which is quite close to the actual. So that means this single differential equation goes quite close to the actual answer compared to thermal equilibrium assumption. Okay, are there questions? Okay, so now let me proceed. So then now we ask the following question. So given this data, given x of t, how do we decide which surface we should call the last scattering surface? So roughly, of course, the idea is clear. Right? The last scattering surface should be such that if there is CMB photon, okay, at that temperature, so it defines some temperature or some time at the last scattering surface. So a CMB photon at that time or at that temperature should have traveled to us today without any scattering. Okay? That's the definition of a last scattering surface. But of course, you have to define it probabilistically, right? Because different CMB photons may scatter at different times. So we'll try to make it more quantitative in the rest of today's lecture. And for that, we'll give some definitions. So we define what is called opacity, O of t. So this is the function of the temperature, okay, of the universe. So this is the fraction of CMB photons so at time t, which we'll think of as a function of temperature, right? I can either think of temperature as a function of time or time as a function of temperature. So this is a fraction of CMB photons at time t that undergoes at least one scattering before it reaches us. So higher opacity means less visibility. Right? Higher opacity means a higher fraction of the photons would have undergone at least one scattering before it reaches us. So we can't really see that surface very well, right? Because the photons are not coming directly from the surface, that region. So this we can actually calculate. Okay, so let me explain how this calculation goes. So let's consider a CMB photon. Time t. And let's define q t prime t as the probability that it does not scatter till time t prime. Then we can easily write down a differential equation for q. Okay, so q t prime t. This is similar to what we did yesterday. dt prime will be minus sigma t net prime q t prime t. So the only difference from yesterday is that now we are going to use for this one not resonance scattering but elastic scattering. Okay, we'll assume that the photons are low enough energy so that there is no resonance scattering, there is no lifting of NL state to N prime L prime states. Okay. But these are all elastic scattering with free electrons. Elastic scattering. With other free electrons or the hydrogen atoms that is formed. Okay, the total elastic scattering cross section. So this tells us that Q, we can integrate this. Okay. Q T naught T is given by exponential of minus integral T to T naught. T naught is today. Okay, so here I should have said this. Perhaps I think this should have been. Okay, so we are talking about this is like what's called Thompson scattering. Okay, because we are assuming that the number of free electrons have gone down quite a bit. Okay, so now there is only elastic scattering with the hydrogen atoms that are left over. Okay, otherwise you have to put also the cross section for, I mean, the full this thing will be this plus we can say sigma c times n e of t prime. You can certainly do that. Okay, but the whole thing should be the total cross section. Okay, we can put sigma c times n e of t prime. So this is this integral that's going to give you the value of q. Okay. And you can certainly do this because you know the population of the 1s state and you know the population of the free electron states. Okay. So you just put them together and then you do this calculation. And from the definition of opacity, it follows that O is given by 1 minus q. Okay. So O of t is given by 1 minus q of t naught t. Because q is the probability that it does not scatter till time t prime. Okay, so here you have taken q t naught t, so it doesn't scatter till time t naught. Okay. And opacity is the probability that it does scatter at least once till time t naught. Okay, so O of t is 1 minus q. Okay. So using this formula, okay, we can find the opacity. Is this clear? Are there questions? So this can also be interpreted in a different way. So 1 minus O of t, which is q t naught t. Okay, so this, you remember, is given by the fraction of the CMB photons at t that reaches us with no scattering. In between. So we can turn this around and we can say that this can also be interpreted as, can also be interpreted as the fraction of CMB photons. Today, that had their last scattering before T or at temperature higher than T. Is this clear? Okay, so this is an alternative interpretation of what this Q tells us. Okay, because this is the fraction of CMB photons at T that reaches us today with no scattering. So its last scattering must have been before time T. So now, based on this, so we can say that the fraction of CMB photons that had their last scattering in the temperature range T and T plus dt. This should be given by minus, O increases with T, so O prime of T dt. Is that clear? Because this is the fraction which had their last scattering at a temperature above T. So if you take a temperature T plus dt, right, then the corresponding quantity gives a fraction that had the last scattering at a temperature above T plus dt. So the difference between the two will represent those photons, the fraction of photons which had last scattering between T and T plus dt. Right? That's what we're calculating. So calculating the difference between 1 minus O of T and 1 minus O of T plus dt. And that's what is the origin of this equation. Is this clear? Okay, so now we can easily calculate this. So O of T, we had this formula, it's 1 minus exponential. We should keep on think of the T and T as interchangeable. So T is a function of T and small t is a function of T, right? So you can just go back and forth between these. So exponential minus integral T to T naught. Let me just ignore the component scattering for now, but we can always put that in. So now if you take the change T to T plus dt, then this small t changes to small t plus dt. So O prime T dt is given by, there are 3 minus cents, 1 minus cent from here, 1 minus cent from there, and then this is lower limit, so that's another minus cent. So you get, first of all, exponential of minus integral t to t naught sigma t n1 s t prime dt prime, and then we get sigma t n1 s of t, and this dt prime, this is dt. Okay, because we are integrating now from t plus dt to t naught. Okay, so that's the overall minus sign, because as I said, 1 minus sign here, 1 minus sign here, and 1 because it's a lower limit. And in this dt, we can now convert to dt prime by writing this as dt small t inverse times d capital T. And this one is, let's do this. So T is T naught over lambda, right? So T dot is minus T naught over lambda square times lambda dot. So that's minus T times H of T. Because T naught over lambda is T, and then lambda dot over lambda is H, right? So that's minus T times H of T. So this I can write as, so this quantity itself is 1 minus OT, 1 minus OT, and then sigma T N1S of T, and then here we have dt divided by T times H of T. Okay, in the next slide, I'll try to write this formula in a better way. Is this okay? Are there questions? So let me write it again. So O prime T is given by 1 minus O of T. Yeah, and the minus sign cancels. Okay, because there are 2 minus signs. Yeah, so there's 1 minus sign here, and this gave you another minus sign. So there's no overall minus sign left. And here you have to always keep regard the small t and capital T as functions of each other, right? So when they say h of small t, if you want to convert to temperature, you basically use the temperature time relation to convert this to temperature. So now recall that O prime T dt is the fraction of photons, fraction of SOMB photons whose last scattering surface, whose last scattering happened in temperature range T and T plus dt. Now, what do you expect O prime to be? What kind of function it should be? Right? So O of T should go to 0 as low temperature, right? Because at late time, almost all the CMB photons that are emitted from late time will reach us, right? So O of T should go to 0 opacity, and O of T should go to 1 at very early time, right? Because there it's almost 100% certainty that a photon at an early time would have scattered at least once before reaching us. So if you plot O versus T, O versus T, we expect a graph like this. Okay, it goes to 0 at both ends. Sorry, not O, O prime. Because O approaches 0 at one end and T at other end, the derivative vanishes. And by the interpretation that O prime of T dt is the fraction of CMB photons whose last scattering was at this temperature range, it's conventional to call this the last scattering surface, where this peaks. Because that means that the maximum fraction of photons that you see today had the last scattering at this temperature. And of course, it's not a sharp surface, there is a variation. And if we just follow this differential equation, the single differential equation, then the dx dt equation, then, okay, again, this is Weinberg's result for omega b h square equal to 0.02. One finds that the peak is at 2954 Kelvin, and then standard deviation is about 253. Okay. So you see that the temperature has, of course, changed a bit, okay, from what we would have expected from the equilibrium values, because we had said here, let's just go back a little bit. You see that 3000 K, right? The X is still 0.154, right? There's a reasonable amount of free electrons left. But this decreases very rapidly. Okay, and that's the important point. Because this decreases very rapidly, what happens is that at the end, the actual temperature at which the last scattering surface is doesn't change very much. Okay, because between 3000 K and a little lower, okay, the number of free electrons comes down drastically. And it's the same reason as in nucleosynthesis, right? Because actually the temperature at which you are doing this, that B1 over T is a huge number. So a small change in temperature causes a large drop in this B1 over T. And that's what is responsible for this rapid change in X as the temperature comes down. So this is what yes, go ahead, please.
If that actually was the case, then wouldn't the right side of this maxima be sharply peaked?
Yeah. So this is, I mean, you shouldn't trust this too much, right? It's just that, I mean, all I wanted to say is that there's a maximum here.
Yeah, but the width is also, like, I would think this is a large width, 10%.
Yeah, well, I mean, you have to do this calculation and check, but that's what one finds. Okay, it could be that this comes mainly from this side.
Yeah.
Okay, so I probably shouldn't have written it in this way. Right? This is the standard deviation, but it could be more tilted on one side than the other one.
Yeah, okay.
But I think once you do this time evolution of X, it should become clear exactly what the shape of the curve is. The other point, of course, is that even though the number of free electrons is falling, right, there is still this Thompson scattering, right? I mean, from the 1s states, okay? And that is falling because that number is going down as 1 over lambda cube, right? Because the universe is expanding, so the density of free hydrogen atoms is also decreasing. So the part of the width could come from there also. Okay, because N1s is not decreasing exponentially; it's actually decreasing as 1 over lambda cube, right?
Yeah.
Has to take that also into account and then do this calculation.
Yeah.
Okay, any other question? Okay, so this finishes part of the course. Okay, so let me say in which part of the course it finishes. It basically finishes the part of the course that is based on known physics. Okay. So this part of the discussion is based on the standard model physics. But you would notice that we didn't really need to use very much of the standard model, right? Because we started at about 1 MeV, right? Between 1 to 10 MeV. That's where we started our evolution and studied what happens subsequently. And the reason for this is that thermal equilibrium erases memory of what happened in the past. Mostly. And this is the reason why we didn't have to start at 100 GeV and follow the history of the universe, because once you assume thermal equilibrium, then most of that information is gone anyway. However, we also have seen that thermal equilibrium cannot give us everything. Okay, some data is needed. So some data have to be provided. Data need to be provided. As initial condition. So for example, the values of the conserved charges. Values of conserved charges. Okay. Or if there are decoupled states, the relic density of states of particles that have fallen out of equilibrium and so on. Now, within the standard model, okay, we don't have any relic density. I mean, one can study, one knows all the particles in the standard model, and one can check that none of those particles really serve as a relic. Okay, I mean, one reason being that there are really no stable particles, right? So anything that is left over during when they're going out of equilibrium, okay, or if they're going out of equilibrium, is basically decay, right? And the only particles that remain here are the neutrinos, which you have already studied, right? That's how we started between this 1 and 10 MeV, because the neutrino decoupling happens there. So values of the conserved charges, again, I mean, we know that we need some data. Oh, I should have said here that even though the standard model doesn't have any relic density, we know that we do have relic densities. So we know that in our universe we have dark matter. So this, from whatever you have studied so far, you cannot say what dark matter is, right, or how they might have produced. And standard model by itself doesn't offer an explanation of what the dark matter is. Similarly, values of conserved charges. Okay, here you know that we have baryon number, non-zero. Standard model by itself doesn't tell us what a baryon number is. Okay, so by going higher up in temperature in the standard model will not tell us what baryon number is. We also have lepton number. Well, we don't know if we have lepton number or not. Lepton number is conserved, of course, in this approximation, but the question is that do we have non-zero lepton number? Do we have non-zero lepton number? Okay, again, Here the answer is that we don't know. We don't know simply because the density of neutrinos is not known. So what I mean by this is that we do not know if there is a difference between new and Newborn numbers. We'll see that the standard model will be able to say something about this. Okay, what it says we'll see later. But basically what this is saying is that if we want to explain the origin of dark matter or non-zero baryon number, we have to go beyond the standard model, which means that we incorporate in the microscopic theory new interactions, new particles maybe, incorporate in the quantum field theory new fields with new interactions. And we will try to do this in a somewhat model independent way, right? Instead of writing the specific Lagrangian, we will try to work with a class of Lagrangians and see what we can say, what kind of new physics could have given rise to other dark matter or baryon number and so on. Okay, so this is something that will be studied next. This will be studied next. Another thing that we do not know within the standard model, within the standard cosmology, is the origin of the perturbation of fluctuations. And this, of course, is important because if there are no fluctuations in the early universe, then we wouldn't be here, right? I mean, the universe will still be uniform. So this also is something that we'll be studying. Okay? But this also requires going beyond standard model, okay, in particular inflation. Okay, so we'll also study this in more detail. Okay? So the rest of the course will be based on physics beyond the standard model, okay, because standard model doesn't give other inflation, okay, at least not in an obvious way, nor does it explain the origin of the baryon number and the non-zero baryon number and the origin of dark matter. Okay, so I think I'll stop here today and then we'll continue next time with beyond the standard model physics. Are there questions? Okay, if not, let me stop this. So I'll see you next week then. I'm ending the session.